So first of all, what is it, right? Well, it means different things to different people, but for the intent and purposes of this discussion and what we're going to go through today, basically an application built on an architecture that can adapt to changing conditions, all right? And why is that? Well, traffic and load patterns are unpredictable, right? If you guys are in flash crowd or viral type events, you don't know what kind of user traffic your site is going to see. So you need to be able to adapt to those dynamic conditions. Rarely are you in an environment where you know exactly how many connections you're going to have that day or any particular moment, right? Particularly when there's a human on the other end, okay? We also want it for availability and reliability, right? We want to distribute that application across multiple components, and we'll talk about what that means later. But to increase the availability, to increase the likelihood that the app is there when your user wants to get to it, right? In the old days, pre-cloud, like 3-4 years ago, there was two ways to do that: over provision and under provision. And over provision is where you'd say, okay, I'm going to buy all the hardware I need for the, I never know to call this best case or worst case, right? Because you got a ton of users and you're using everything. So I guess that's best case. But you buy a bunch of hardware and you prepare for the case where you have the most amount of traffic, right? And in the normal case, you got a lot of idle hardware sitting there, right? And that's wasted dollars, right? The other option is to under provision. Provision just enough hardware to handle the steady state or normal case, right? In that case, everything's fine for most of the time. But if you happen to have any of these, viral events, or you get slash dotted or dug or something like that, you're going to miss opportunities. End users are not going to be able to get to your product, not going to be able to get to your website. So what we say around RightScale is don't be a victim of your own success, or don't be a success disaster, right? Don't have some incredible success that brings everything down, okay? And I'm sure we've all heard of examples of sites that have suffered things like that, okay? The over provision and under provision model, right? Anybody that's seen any of Michael Crandell, our CEO's talks and sort of the general cloud concepts may have seen this traditional hardware model slide before, but it bears kind of repeating is that what you see on the blue line there, it's what do you call it, infrastructure cost, but you can basically think about that as servers. How many servers do I have, right? So the blue line shows, hey, I've got a bunch of servers, I dump a bunch of money, I have some more servers, I dump a bunch of more money, I have some more servers, right? The predicted demand is that dashed orange line, and as you can see, the red line is in our farcical example, but it could be, it is realistic, is our actual demand. Rarely can we actually predict the demand correctly, right? So in this case, what you see with that green line is we have all this hardware that's available, all this infrastructure that's available, and no one's using it, right? So I've wasted my dollars. I have wasted infrastructure costs there, right? And then the other case, the under provisioning case, as we said on the previous slide, is what you see in the shaded box there, right? Where you have this demand that you can't meet because you don't have the infrastructure to handle it, right? That's the old school way, right? New school, the cloud resource model, right? You can dynamically provision what you need when you need them, okay? If your demand goes up, you throw more resources. When your demand goes down, you tear them away, right? We're all familiar with that as far as the cloud is concerned, and that's the true utility computing aspect of it. You pay for what you got when you flip the switch, and when you turn the light switch off, you're not paying for it anymore, right? So with that said, that previous slide looks more like this in the scalable cloud model. We've got the same prediction and the same actual, but as you can see here, using RightScale's alert and monitoring system, you can go ahead and dynamically allocate those resources to stay ahead of that demand, okay? So you never have this opportunity lost. You always have the capacity to meet the demand that you have, yet you're not over-provisioning by a great amount and wasting those resources, right? So this is where we all want to get to. When? Well, we're all here today, right? There's no time like the present, right? The tools are available. Let's go ahead and make use of them, right? And the how? All right, that's what we're here to talk about. So the rest of the talk, we're going to be referring to this reference architecture. So I'll spend a few minutes just to make sure it's clear. It probably is. Most of you are probably familiar with something similar to this at least. But basically what we have here is DNS sending your users, typically via round robin or whatever your DNS provider provides, to your front ends, right, to your load balancers. And in this example, we have the load balancers are talking to two fixed or persistent app servers that are always around, as well as an app server array. And that's represented by that app server 3 through N. That's the scalable part of the scalable web app, right? We can go ahead and throw more servers into that array, and that's might be a RightScale terminology, but it's kind of a fairly common concept as well, is that we have this server array, we can throw servers into it, and we can take servers away, right? These load balancers can distribute the load that they see to any one of those application servers, again, typically in a round-robin fashion. App server 1 and 2 may be encapsulated in that server array as well. It all depends how you want to set it up. And we can talk about array minimums and maximums and all this kind of stuff. In this example, you'd have a minimum of 2 app servers running at any time, right? We can also set up other environments where you have 1 or 0. Doesn't make a lot of sense, but you could do it. Behind the app servers, we have a caching tier, right? Typically, we have a cache set up so that to take the load off the database, right? If we don't need to hit the database, we shouldn't. And you heard Corey here talk a little bit about scaling the database tier is the hard part, right? The rest of this is relatively straightforward. So let's try to take the load off the DB as much as we can so we don't have to deal with the hard part, right? But the cache isn't always going to have what we need. The answers aren't always there. So we need to go ahead and we need to get to the database. And typically what our customers use, and we'll talk in depth at the end about all the different database technologies and the options here, but the classic one at least that a lot of our customers use is a master database with an attached storage that's replicating to one or more slaves typically in multiple availability zones, and that's for availability and reliability, right? And we'll talk more about that as well as we go through. And they're all taking snapshots of their data. They're all backing up their data to some redundant, persistent storage, such as S3 or cloud files or whatever the cloud provider that you're working on provides, okay? So let's start at the load balancing tier. We'll start at the top and work our way down. ELB or not ELB? That is still the question. And for those of you that aren't familiar with AWS and their terminology, ELB is their elastic load balancer. And up until about, and I have no longer the case as of mid-October, these are slides I used to use. And about October 12th or October 14th, something like that, the first two items there went away. You used to not be able to do SSL termination on the ELB, and therefore you could not do session affinity or session stickiness on those secure connections. In mid-October, they've announced that feature, and it is now supported. So those two have kind of gone away. The ELB can scale up to handle large amounts of traffic, but it is slow to ramp up. And make a mention here, the last bullet point is that we have a technical white paper that we wrote on the load balancing solutions that compares ELB and a bunch of others. And there's a link at the end to tell you guys where to get that if you want more information. But basically what we found is that we got bored with throwing traffic at it because it was able to handle it all. We were basically infinitely scalable. I'm sure at some point we hit a threshold, there's no more capacity or AWS cuts us off, but we got bored of waiting. But the point was it was slow to ramp up. Yeah, it got there and it could handle these 20,000, 25,000 connections we were throwing at it every second, but it took it a while to get there, okay? So that can be a caveat and a problem. We'll talk about that in the next set of bullets here. The nice thing is you only need one. You create an ELB and it's out there in front and it's handling all of the traffic that you need, okay? The second option that a lot of our customers use is HA Proxy plus Apache. This can handle SSL termination with the addition of Apache in there. So you can handle that SSL termination at the front end. It allows for sticky sessions, this session affinity with those secure connections. The beauty of it is that each instance can handle a specific amount of traffic with no ramp-up time, right? The downside is each instance can handle a specific amount of traffic, and that's all they can handle, right? So what we mentioned there is that, the way I look at it as ELB starts with this little pipe, and you throw traffic at it, and it can slowly grow up and become as big a pipe as you need. HA Proxy and Apache, the pipe's always this wide. You can use this much of it, you can use the whole thing. But once you go beyond here, you need another pipe, right? So that's sort of the difference of it. So addition of load balancers is possible, right? So you can always throw additional ones in there, and we'll talk about best practices around that in a minute. But it does require some DNS modification. So typically what I tell customers is that it used to be, if you needed SSL, that's now out of the question, but if you have spiky traffic, if you guys are in environments where you see flash crowd events or you see viral events, and all of a sudden you guys can go from 1,000 connections a second to 50,000 connections a second, ELB won't be able to handle that in a quick amount of time. It'll be able to get there over time for sure, but it won't be able to handle that immediately. So really it boils down to the type of traffic that your site sees. And you'll see this common theme through the talk as well as we talk about run performance tests, run load tests, and do benchmarking and figure out what's normal for you and what you guys can handle. Yeah? Load balancer plus an application server. And for those of you that have been on our support site, you see that sort of our tutorials, some of our welcome to RightScale kind of tutorials have this, right? And they have the concept is you have the load balancer and the app server co-resident on the same instance. And it's definitely possible, and it's great for test and dev. It saves money. You don't need to have these extra instance hours for the extra instances that you have running, but we don't recommend it as a best practice for a production environment, okay? And the reason is that you have these traffic spikes, you have these unpredictable events happen, then all of a sudden this instance is no longer good at load balancing, nor is it good at being an app server, right? You've now kind of hobbled it. So it really makes sense when you can separate functionality, and therefore you can scale those tiers independently because you might not need to scale them at the same rate, okay? So our recommendation, if you're not using ELB, for example, minimum of 2. We always recommend 2, even if you don't have that, your traffic needs aren't that great, right? Again, for availability, reliability, you want that redundancy. Each load balancer should be in a different AZ. And again, to increase that reliability and availability. We've done a lot of testing in this white paper I mentioned. You can see all the gory details and all the numbers, but an M1 large has turned out to be a real good choice, an AWS M1 large for the load balancer. There's about 100 to 120,000 packet per second limit, sort of the speed of light, if you will, through the virtualized infrastructure on AWS. So larger instances don't get you beyond that 120K PPS. So throwing an M1 extra large or even an M2 quad XL we used did not get us any better performance because it wasn't CPU or memory constrained. It was virtual NIC, right? Basically your virtual interface constraint. So we found that those M1 larges there was no reason to go beyond them, I guess is what I'm trying to say. We're able to handle with a real low packet payload. I was requesting like a 147 byte page, and it really was just how many requests per second can I crank through this thing. We roughly saw about 5,000 responses a second for an M1 large. So what we recommend is figure out how much traffic do I have, how much traffic may I have, what's my worst case, divide that by 5,000, that's how many you should have, right? If that number works out to less than 5,000, we still recommend you have 2, so you have that redundancy and availability covered for you, okay? The app server tier, as we said in the reference diagram, that puts the scalable in your scalable app, right? This is where rubber hits the road as far as scaling goes. And you really do need auto-scaling in any dynamic environment, right? If you don't know the kind of traffic you're going to see, you're going to have that under-provision, over-provision problem that we talked about earlier, okay? So we're going to delve into this app server tier and the server array in particular, okay? Okay, auto-scaling, what do we mean by it and how do we implement it, right? Well, what we mean by it, fully automated server launch based on some auto-scaling triggers, right? You have to be able to have a server come up with no manual intervention. You need to be able to have this thing become fully operational without you having to touch anything. It join the pool, talk to the load balancer, say, hey, I'm here and I'm ready, and nothing has to happen other than, you know, you're just setting up your triggers appropriately, okay? As such, we have typically recommend that you download and install your app code from some common repository, SVN, S3, Git, whatever it is, right? But you want them all to download from the same place, the same file, so when they come up, they're identical to their siblings. There's no difference between these instances, right? And that's important so that you always have the same code being served by every app server within that tier, because when traffic comes in and you get load balance, you don't know where that traffic is going to go, right? So a little bit about these triggers. Okay, what can be the triggers that cause this auto-scaling to happen? We have some sort of common ones and then some custom ones. The common ones, most common one by far, is CPU idle. Basically, if the CPU is not real idle, it means I'm getting busy, send me some help, right? Spin up some more servers, send me some help. Also, free memory and system load. If you guys are familiar with the top command, the load.midterm is a very common value that our folks use as their auto-scaling trigger. We can also do custom metrics. For example, part of the RightScale platform we provide with Apache is a web server connection plugin for collectd, and you can actually use web server connections as your auto-scaling trigger if that's relevant for your application, if that's where your pain point is, right? But you can also add application-specific metrics using a custom collectd plugin if your app can be queried to spit out a value, you know, number of users logged in or some other metric that's pertinent to your application. If you can query that, get that value out, we can graph it, shown on one of those pretty graphs you've seen a couple times today, and we can also use that as your scale up and scale down metric, okay? When to scale? We say conservatively up and down. And what do we mean by that? Well, up, you want to allow adequate lead time for your servers to become operational. In the previous talk, when Raphael was talking, someone had asked a question, how long does it take an instance to spin up, right? And one of them was 5 minutes and one of them was 15. You need to know what those metrics are for your servers so that if it takes you 5 minutes, you want to make sure that you call for help more than 5 minutes in advance, right? You want to make sure that you have that lead time to allow those servers to come up and start contributing to the overall goal. You want to do it before your system is negatively impacted. You want to look for trends and act early, all right? You don't want to act late because you're going to have those missed opportunities, all right? And what's the worst that can happen? What's the worst if you spin up a server that you didn't really need? I was too conservative, all right? Well, I spun it up, and then the next hour I'm going to spin it down. I'm going to scale it back down. So I ended up being charged for 1 extra hour, right? An M1 large cost me 34 cents. That's a pretty low price to pay to have that little security net, okay? In the down direction, same basic concept in reverse, right? When the system has been underutilized for a consistent consecutive period of time, you don't want to have little spikes of drop-off and stuff like that, but you want to see nice consecutive drop-off of traffic. And again, that can be CPU or load or whatever it may be. And I think Josh, if you guys were here for the first talk, talked a little bit about this as well in an array. We typically recommend that you scale down fewer servers than you did in a scale up, unless you're doing a one-to-one. If you have a fairly simple deployment where you're adding one server and taking one away and you scale up and scale down, that's fine. But some of our customers, like the social gaming folks, right, they come out with some new feature and they get hammered. They'll spin up 50 at a time, right? So they'll have a scale-up event where they'll add 50. Well, when they scale down, they might pull down 30 or 25 or something like that. Again, they're being conservative, right? Let's tear those down because, again, what's the worst thing that can happen? All right, I left it running for an extra hour and it cost me a couple extra pennies, all right, for that safety. So, again, better safe than sorry, okay? Okay, some considerations about this server array. We recommend that you weight the array across all availability zones, and I say not regions here. We'll talk about that, okay? As we've said many times, it increases the reliability and the availability of the application, right? If US East 1A goes down, well, you got B, C, and D there to help you out, right? The most you've lost in East is 1/4 potentially of your application servers, right? 2 notes here. Currently, traffic within an availability zone at AWS is free on the private IPs. On the 10. Network, you can talk to each other all you want for free, okay? If you traverse to the public IP, you have to pay their public IP rates. But traffic between availability zones incurs a per gigabyte charge. It's nominal. It's currently like a penny a gigabyte, but there is a charge there, okay? So that's something to keep in mind. Traffic between regions, US East to US West or EU or whatever it may be, that's charged at those public internet rates, plus you have unknown latency, right? You're out in the Wild West at that point. You're not on AWS's fiber channel anymore. So that's not a recommended best practice, okay? Because cost and latency issues, okay? We talked a little bit early on about minimums and maximums. Set your minimums and maximums appropriately. Your minimum can assist in cost savings, right? Maybe you have a game, and between midnight and 6 a.m., nobody plays your game, right? So set your array minimum to 1. So in the middle of the night, you got 1 server in case there's some insomniac out there that wants to play your game. He's got some server he can get onto. But you're not exposed to having 10 or 20 of these idle servers running, okay? And then set your maximum. That can limit your overall exposure, right? I don't want to ever pay for more than 50 M1 larges, and I've got my array running on M1 larges. So set your max accordingly, okay? And that can help you on the cost side, savings both directions, okay? The instance size. And this is, again, a lot of what we're talking about here is AWS specific, but obviously it depends on the cloud provider that you choose and what the service offerings that they provide. But we found that an M1 large is usually a pretty good choice for an application server in an array. It provides you like 7.5, you usually get about 7 gig of RAM, plus it's got some pretty good CPU characteristics. So that's a pretty good, relatively beefy member of your overall contributing society, right? We have seen folks use M1 smalls and even micro instances. Those are great in test and dev. For example, the T1 micro, whatever they call it now, there's 64-bit versions of that. So for example, if you have, you're using a 64-bit JRE on your M1 large and you want to make sure you're using the exact same code, all right, you can use a T1 micro now and use a 64-bit T1 micro in your test and dev environment, things like that. Every app is different. Run those load tests, bang away on it, see what's right. Run it with M1 larges, swap them out, run it with M1 extra larges. Maybe in a particular load you need 10 M1 larges, but you only need 2 M1 extra larges. All right, well then look at the prices, do the math, and figure out which way works best, right? So again, benchmark, load test, figure out what's right. Every app is a little bit different, so there's no silver bullet. You have to worry about code deployment in array considerations, right? If you have, some of our customers have literally hundreds, one of them even have thousands in an array. And now all of a sudden I've got a new version of code and I've got to push it out to 1,000 servers, right? How do I do that, okay? RightScale has the tools within the platform to allow you to run a particular script on any server or any servers in a deployment. So you can say, hey, I want to run this script on every server in my array, and maybe that's your SVN code checkout script. And that goes out to SVN, sucks your code down, puts it in place, and you're good to go. So that's another thing to consider always with your array is, okay, I've got all these servers out there in the wild, I need to update them. We do provide you tools to do that. Caching tier. As we talked about at the very beginning, it can dramatically decrease the demands on the database, right? The database is the hard part. Let's try to take the load off that as much as we can. Very helpful, particularly in read-intensive apps. And we'll talk a little bit about write-intensive apps and their peculiarities here in a minute. But the cost of caching. There is some application complexity and modification, right? So for example, in the old days, the old version before the cache, you would say, okay, this app server needs something from the database, read from database. Okay, well I now have to change that section of code. It's now read from cache. It's not in the cache. Read from database like I was going to do anyway, write it to the cache and go on my merry way, right? So yeah, you have to modify your code a little bit, but it's pretty straightforward and pretty easy. And then obviously there's the additional instance hours. You have this caching tier running with these additional caching servers. and you've got to pay the instance hours to support those additional instances running within the cloud. Okay? Our recommended best practice is to have a separate dedicated caching tier, all right? And I'll talk a little bit about the sub-bullets here. And some of our users have done this, but in very specific use cases. You can implement caching on each app server. So for example, you can spin up an app server and it can have your PHP, you can install PHP on it and install memcached. And that's fine, but we only recommend that that server uses the co-resident cache for itself, and it's not part of the distributed cache because there's application complexities and database performance degradation if all of a sudden you have caching servers coming in and out of this caching tier, okay? So in very specific use cases, this might make sense. We generally recommend you have a dedicated caching tier that you use as a distributed cache, okay? Instance size and count. It varies, right? That's the answer a lot of times. What should I use? Well, it varies. What we always recommend is determine your memory caching footprint. So for example, let's say you go, okay, in my deployment, my scalable web app, the worst case is I'm going to need 30 gig of cache. That's the worst, that's the most I'll ever need. Okay, well let me see, that would be roughly 4 or 5 M1 larges. They give me about 7.5 gig of RAM. Okay, well then we always recommend that you over provision if possible. You want to have room to grow into what you hope will be your best case with your most user traffic. And therefore you can select the instance size and count that will give you that overall caching footprint and distribute it. Again, I hope I have it here, yeah. Distribute that across your availability zones to increase your reliability, increase that availability of the system, okay? And like I said, we recommend that you over-provision so that you have that ability to grow into it, okay? The other nice thing about this is that if you lose a particular caching server, you've only lost 1/nth of your cache, right? For example, there's M2 Quad XLs right now in EC2 that are 68.4 gig of RAM or something like that, right? That's probably more cache than you'll ever need. But if you throw all your cache on that one server and that instance goes down, there's your whole cache, right? So again, we recommend you distribute it across multiple nodes to prevent that single point of failure. All right? And we say to over-provision because you can manually scale caching servers. It's not something you can really do in an auto-scaling environment. And it is possible, but it's non-trivial. It involves application and database performance degradation because you add a new caching server, you have to inform all the app servers that it's there, and that typically requires an app restart or some reload or something like that, and it's usually a non-trivial event. And more importantly for the database is it has to redistribute the data objects, right? So the analogy that I always use is that think of it as a card game where the caching servers are the players and the database is the dealer, and whatever card game this is, he deals the entire deck. So you've got your 4 players, your 4 caching servers, all the data objects are distributed. Now we add a 5th caching server. We have a new player in the game. Well, the database sweeps up all those cards, all those data objects, and he has to redistribute them to all the players in the game again. That's a huge hit to that database, right? So that's something you want to avoid. You can't always, but you want to try to avoid it when you can. Time to lives, the TTLs. We always recommend that you set those. You can set those to indefinite in memcached and other applications. We recommend you always set them to expire because if you did end up adding a new caching server or whatever, you now have this new hashing algorithm, and maybe this object that was on server 1 is now hashed to server 2, but it's going to live in the memory of server 1 forever because you didn't set that TTL appropriately. You can set them to long if you want, long time, but make sure you always set them to timeout at some point, okay? Write-intensive applications, what do we do about those? Well, granted, they don't see as large an improvement, right, because they're not reading, they're writing by definition. Tools such as memcached, right? Memcached is an open source project. So you can modify that. You can use that to basically do lazy writes to your database. So instead of writing to the database, you write to memcache, and there's some cron job or something similar that occasionally comes along and sweeps up and ships everything down to the database in one big write instead of a lot of little writes, okay? Bad parts, data can be lost, right? If you have that caching server like that and it's in a dirty state and all of a sudden it dies, all right, you've lost all that data, okay? Therefore, it's not a recommended best practice, but some of our customers are doing this, and I just wanted to point that out. And depending on your use case, maybe it does or does not make sense. The trade-off here is performance versus the end user experience, right? I'm playing my game and all of a sudden my caching server goes down and I've reverted back a few minutes because you didn't write my changes or something like that. So again, not a recommended best practice, but we do mention it because some folks are using it with some success. We also have third-party providers that RightScale is partnered with, such as Membase, and we have some others coming online as well. And these are vendor solutions that allow you to dynamically scale that caching tier. Okay, so that's another option that is forthcoming. That is forthcoming, okay? There are a lot of architectures that exist for the databases. I'm sure you heard from Corey and others. And again, no one-size-fits-all solution, right? So again, we always recommend you do load testing and you do your benchmarking and figure out what is optimal for your particular solution, your particular situation, okay? So let's go through and talk about a few options here. The first one, the classic one a lot of our customers use is master and slave or slaves if budget permits. Multiple slaves always recommended if budget permits. Again, just increase that reliability and availability, okay? Distribute them across availability zones in case there's some catastrophic event in a particular AZ. And always use the same instance size for masters and slaves. We have customers that come to us and say, hey, I really want to save some money. I've got an M2 XXL and it's costing me $1.60 an hour or whatever it is for my master, and my slave is doing nothing other than replicating from it, and it's costing me $1.60 an hour. It's like an insurance policy, right? I've got a $1.60 an hour insurance policy that I hope I never use. Well, what if I use an M1 large? It's still a 64-bit architecture, and it can handle it. Well, you probably chose that master size, that M2 XXL, right? You chose that for a reason. It was big enough for whatever you needed, okay? What happens when your master fails, and now all of a sudden you need to promote this slave to be your master? You're now promoting an underpowered slave to be your master, and now all of a sudden all heck breaks loose because you have application performance degradation, database degradation, you've got to scramble to bring up a new master of the original size and all this kind of stuff. So yeah, it costs more money, but a highly recommended best practice is use the same instance size for those masters and those slaves. Data storage. Use EBS volumes or whatever the equivalent is in the cloud provider that you're working with for that data store. Never use that ephemeral or local storage, because if that instance goes down, that data's gone, right? So make sure you use that more persistent EBS type storage. Back up the master and slaves frequently, obviously. The RightScale MySQL templates, I think by default, do the master every 4 hours and the slave every hour. That's modifiable, that's configurable via some inputs. If you guys saw Raphael's presentation, he showed you some of the inputs on the server template page. And we recommend you always upload those database backup snapshots to S3 or cloud files or whatever, some persistent redundant storage. So if bad things happen, you've got a way to get back to where you were, okay? Instance size. It varies greatly. I mean, it really depends, okay? The answer is here is it depends, okay? Your application, the type of traffic you see, are you write intensive, are you read intensive, et cetera. That's going to dictate what the right instance size is to start. So again, do that load testing. Run Apache Bench, run HTTP perf, bang away at it and see what's right for your particular. Swap in components and see which one works best, okay? Try to find where that sweet spot is for your particular app. And for those of you that saw Corey's talk, he talked a lot about this, and we're going to talk about scaling in 2 dimensions, or directions. Vertical, and that's kind of the concept of growing or shrinking the database instance size, right? Maybe you have that M1 large, and all of a sudden it's underpowered, and you want to move it up. You want to take that same database and move it up to an M1 extra large, or an M2 XXL, or something like that. So vertical is the ability to grow or shrink. And horizontal is, as Corey had said, it's the ability to add nodes in a horizontal manner to help distribute that database, to help distribute the load across multiple nodes, okay? And so a quick sort of pictorial representation, as I stole this from one of the marketing slides, so that's why it's got the, about how easy we make everything and all that. But the concept in vertical is you have these servers of small type A and small type B. You have the same quantity of servers, you just have bigger versions of them, right? Whereas in horizontal scaling, you keep the same sizes and you just add more of them, right? So we've got 2 small A's and 2 small B's, right? Horizontal, that's where it gets more interesting, right? What can be done and what some customers do is the addition of read slaves. And that's obviously effective for read-intensive applications. Write, not so much, but read-intensive applications. Only the writes need to access the master, right? And you can distribute those reads across the slaves. You do need to worry about replication lag, which Corey talked about as well. If you have an application that does a write to the database and then very quickly reads that data object, or potentially could very quickly read that data object, replication may be an issue. So maybe that's not the perfect fit for you. But if it is, a lot of our customers have used something like MySQL Proxy, right? And for those of you that aren't familiar with it, basically you have the concept here pictorially represented as you have your app server tier, your arrays, your app server array. Instead of talking to the master DB and then replicating to the slave, they talk to the MySQL Proxy server, and that MySQL Proxy server says, okay, this is a write, I'm going to send it to the master. But if it's a read, I'm going to send it to, in a round robin, there's other algorithms, the most common one is round robin, I'm going to send it in a round robin fashion to all the available slaves. And that way, 1/nth of your read traffic goes to each and every slave. So that can obviously help you distribute that load quite a bit. What I haven't drawn here, and it's hopefully implied, is that each of these slaves is replicating from that same master. Okay. So that's sort of a pictorial representation of MySQL Proxy. The other one is sharding, and if you were here for Corey, he went in much more good, nice, happy detail than I will, but basically for those that weren't, the concept is to slice the database, right? Slice those tables into sort of horizontal pieces, if you will, and put them into groups of rows. You do have to put some thought into how you're setting up the shards, since as Corey talked about, cross-shard joins can be resource intensive. So there is some forethought you have to put into a sharding implementation, but great benefit can be gained, okay? So here's two quick slides on sort of a pictorial representation. You know, the old school, got a single app server or multiple app servers, right? Talking to a single master database, and Corey used customer number, I'm using customer name. So all the rows there from A to Z are in that single master database, right? After you've sharded it, you have that app server talking to, and I probably should have drawn a box around all these because it's really one master database that is created by these 4 shards, right? But basically you've broken out your A through E's go to one shard, your F through M's to another, et cetera, okay? So now all of a sudden the load has been broken up into 1/4 of what it was before, which kind of corresponded with Corey's demo on that, the family builder case that he talked about, okay? So sharding is another option. No discussion of horizontal scaling would be complete with good old master. As the name implies, you have 2 or more master databases involved. Any master can modify any database object, right? It's not just a single master anymore. Replication lag can cause some serious problems here, okay? And poorly designed apps that don't have any rhyme or reason as to where they write their data can cause all kinds of problems. And you can end out with databases in inconsistent states, and you might end out with, I have 2 masters, one of them's right and one of them's wrong. I don't know which one, right? So as a result, we don't recommend this, okay? But we do mention it because we do have some customers in very specific use cases that have had some success with this, okay? Not supported by our tool set or anything like that either, okay? NoSQL. We should obviously talk about NoSQL. That's starting to get more and more traction in the industry. A lot of options exist. I've listed just this morning just a few that came off the top of my head. SimpleDB, Membase, Couch, Mongo, React. There's a whole slew. Like Corey said, there's one every couple of weeks that's popping up. Most of the customers that we see that use these use them as a key value store. They can also be, you know, document data stores and things like that, but typically it's a key value store. I've got a key, I want to go down and find something, right? That something might be a huge blob, but it's a something that I'm looking for, right? No complex operations, right? It is not a relational, it's not an RDBMS, it's a no RDBMS, right? It's just basically a key value store. So it's not pertinent for all applications, but for some it may be, okay? You have these multiple nodes to implement that distributed data store. The backup and recovery can be complex, right? Because you want to make sure that you're taking your database snapshots at the same time, or if you're not taking them at the same time, you have some way of finding that point in time where I need to recover to this particular point in time, and these weren't all my snapshots weren't at the exact same moment, so I have to replay logs or whatever it is to catch certain bits and pieces up, okay? Some of our customers are beginning to use some NoSQL solutions in specific use cases. We're starting to see more and more requests for that, particularly in the social gaming area, which a lot of our customers live in. So what's best? Well, as is typical in a lot of these, right, it depends, right? There is no perfect solution, right? And there is no perfect solution because the apps are all different, right? A lot of scalable environments share some of the things that we've seen here, but every app is different, and like I said, there's no one size fits all, but hopefully components in a reference architecture such as like we've shown today, you can kind of draw some ideas from that, and using load testing and performance testing and benchmarking, you might be able to find the bits and pieces that work best for your particular app. And again, we recommend swap pieces in and out. Do your load tests, swap pieces in and out. See what that perfect or optimal solution for your particular application may be.